All right, today we're putting on our detective hats to solve a classic programming mystery, the case of the missing number. We've got our clues, we've got the rules, and we've got a jumbled list of numbers where one key piece of evidence is gone. So let's dive in.
So here's the central puzzle, right? Imagine you get a totally random pile of integers. You got positives, negatives, maybe some zeros, all mixed up. Your mission is to find the smallest positive number that isn't in that list. Sounds simple enough, but, the crime scene is always a bit messier than it looks.
Okay, let's look at some of the evidence right here. Here's our array: 3, 4, -1, and 1. So we see a 1, but wait, where's the 2? Then we jump to 3 and 4. So yeah, pretty clearly, the first positive number that's missing from the sequence is 2. Our job is to figure out how to teach a computer to see that and to do it fast.
Now, every good investigation has rules, and ours are really strict. First, our solution has to run in what's called O of n time. All that means is that the time it takes should be directly related to the size of the list. So if you double the numbers, it should only take about double the time to solve. And second, it has to use O of 1 auxiliary space. This is a big one. It means we can't just create a whole new, big, clean array to help us out. We have to work with the evidence we've got, right there at the crime scene.
Every detective starts with the most obvious lead, right? In our case, that's our first suspect. It's a method we'll just call brute force. It's super straightforward. It's what you'd probably think of first. But does it have an alibi? Let's find out.
So, how does this brute force method work? Well, it's a pretty simple three-step plan. First, it just takes all our messy numbers and sorts them into a nice, neat line. Then, it just strolls down that line, checking each number against the one that comes next. And it's looking for a gap. If it goes from 1 straight to 3, boom, it knows the missing number is 2. Seems logical, almost foolproof. And this is where our suspect's whole story just falls apart. Remember those rules? The solution must be O of n. But sorting, well, even the best sorting algorithms run in O of n log n time. And for a big list, that's a whole lot slower. So right there, our main suspect breaks rule number 1. Brute force is just too slow for this case. We need a much cleverer approach. So, when that first lead goes cold, a good detective has to find a new angle, right? That one little piece of insight that changes the entire investigation. And in this case, we have one. And trust me, it's a total game changer.
Here it is. This is the core insight, the aha moment. Just think about it for a second. If you have an array with n numbers, let's say 4 numbers, what's the smallest positive integer you could possibly be missing? Well, in the absolute best case scenario, the array is just 1, 2, 3, 4. The missing number would be 5, right? Which is n plus 1. In any other situation, the missing number is going to be smaller than that. This clue is huge. It tells us exactly where to focus our search. The answer has to be somewhere between 1 and n plus 1.
So with this new clue, we can come up with a whole new strategy. We're not going to sort the evidence anymore. Instead, we're going to organize it. We're going to perform what I like to call the evidence shuffle.
Now here's the truly brilliant part. We're going to use the array's own positions, its indices, as a set of evidence lockers. So the number 1 belongs in locker number 0. The number 2 belongs in locker number 1, 3 in locker 2, and so on. Our whole goal is to put every single positive number that's in our range into its correct spot.
Let's walk through this with our original array, step by step. We start at the very first position, index 0. What's in there? It's the number 3. Well, according to our system, the number 3 should really be in index 2. So this piece of evidence is in the wrong place. We need to swap it with whatever's sitting in index 2 right now.
Okay, so after that swap, index 2 now correctly holds the number 3. Perfect. But index 0 is now holding -1, which is basically junk evidence we can just ignore for now. So let's move on. At index 1, we find the number 4. Well, that belongs in index 3, right? So let's do another swap.
Now check this out. After we move the 4, look what popped into index 1. It's the number 1. And where does the number 1 belong? All the way back in index 0. So we do one more swap. And we just keep doing this shuffling until every number is either in its rightful place or it's a piece of junk evidence we don't care about, like a negative number or a number that's too big.
And here we are. This is the result of our big shuffle. Take a look. Index 0 has the number 1. Perfect. Index 2 has the 3, and Index 3 has the 4. Every piece of relevant evidence is now filed away, right in its proper locker.
So the shuffle is complete. All the clues are neatly organized. Believe it or not, the hard work is done.
All that's left is to inspect our handiwork and identify the culprit, our missing number.
Okay, so now we do one final, super simple sweep of our evidence lockers. We start at locker 0, and we ask, hey, do you have the number 1 in here? Yes, it does. Okay, we move to locker 1. Do you have the number 2? No, it's got that junk -1 in it. Bingo. The first locker that doesn't have its matching number, that's our solution.
The logic is just undeniable, isn't it? Since locker number 1 is the first one that isn't filled correctly, it means the number that belongs there, which is just the index plus 1, that's the number we've been looking for this whole time.
And there it is. The first missing positive integer is 2. Case closed.
So why did this clever method work so well? Well, first off, it's fast. I know it seems like we could be swapping forever, but each swap puts at least one number into its correct final home. So we're never going to do more than n swaps. That keeps us right inside our ON time limit. And second, it's so efficient. We did all that shuffling right there in the original array, without creating any extra lists. That satisfies our O1 space rule. It's just this beautiful, elegant solution that follows all the rules.
You know, the biggest takeaway from this whole case isn't just the answer, but it's the method. We solved this by cleverly using the array's own structure, its own indices, as a tool. And that leads to a final question to chew on. What other really complex problems out there might actually have a simple solution, just hidden within their own constraints?